So we're going to do like shapes that are connected together. So you might have a rectangular prism with a square prism next to a triangular prism or something like that. And you might have a sphere on top of a prism. It could be anything like that. Just shapes on top of shapes or connected together. And then we're going to slowly kind of apply those things to real life questions, like what you'll see in your practice booklet. When you're trying to figure out the surface area of a composite shape, where you have shapes against shapes, you're going to have overlap region. That's what today's about. Today's about figuring out the overlap in between two different things. We call it the area of overlap. That's what this whole lesson will be. If you look, they have a nice little shape here on the right. They have two prisms right here, where it's one against the other. And they've left the overlap area blank and white so you can kind of see it. The overlap area is this side of the smaller prism, and it's against that bigger prism. I call that overlap. To calculate that overlap can be tricky, but it can be pretty straightforward sometimes too. The best way to do is we're just going to do some examples. So we're going to jump to example 1. It says complete the following for the composite shape if each cube is 1 centimeter by 1 centimeter by 1 centimeter. So if you look down here, I just need to zoom out a little bit. Example 1 is talking about this shape down here, all these little cubes. And they've told us that every side is just 1. So when you're looking at this cube, one side length is 1. And they're all the same. So each line equals 1 centimeter. Awesome. If I want to calculate the area of this, yeah.
Would you just add, because if all the squares are the same shape, would you just count up how many squares there are and add them all up?
Yeah, that's exactly what we're going to do. So what we're going to do is just start with just one face. So if you look and we try to calculate just one square on one cube, this guy right there. The area of that would be length times width. Length times width. On that square, each side is 1, so that's 1 times 1, which means the area of one face is 1. 1 centimeter square. Awesome. Question B. The number of faces that overlap. So if you're looking at this shape, we want to count how many faces are against another face. If we're looking, they've kind of broken up the thing so you can kind of see it. It's like an exploded view of it. It might help you a little bit to be able to see where things are connected. I'm going to point out one that's kind of obvious to me. So on the top, in here in the blue, if I imagine this face right here where this blue line is that I'm drawing, it's kind of back there, right? That's two faces against each other. If I'm looking at it over here in the exploded view, it's this guy that I'm coloring in blue. That would be one face that would be overlapped. Yeah.
Wouldn't it also be the bottom one that's being overlapped?
Yeah, so when you're doing overlap, it's the top of that one, but it's also the bottom of the one above it, right? So when I talk about this being an area of overlap, there's also a side right there on the bottom of that cube that's also being overlapped. So if I was trying to count all the faces that are overlapped, I would have, I'm going to point with my fingers over here. It's kind of hard to do with my pencil. I would have 1 here, 2 there. Looking over here, there'd be a 3rd one right here, a 4th one right here, a 5th one, a 6th one, a 7th one, an 8th one, a 9th one, a 10th one, an 11th one, a 12th one, a 13th, a 14th, a 15th, a 16th, a 17th, an 18th. There'd be 18 total faces that are against another face or another overlapped region. It's a lot, right? Again, if you look at the exploded view, it might help. So like this is overlapped, but then so is this side in here. Can't really see it, but that one is overlapped as well because they're against each other. Awesome. In the decomposed object, shade in any faces that would not be visible in the original object. So if we're looking, I've already shaded a couple. It's hard to shade them all because you can't see them all, but I'll shade the ones you can see. And then we also have some of those sides that you just can't see them, right?
Why on the left side of the arrow, when it all bunches together, why did you count the bottom middle lines?
Like why am I counting right here?
No, like the ones going down.
Like this. Sorry. Like why was I counting faces in here?
Yeah, why on the bottom? Where did you count it?
2. For these guys, I counted it because this is like in here, like this spot right here, and it's against this side of the brick, right? They went together. So that's why I said 1 here, 2 here. Because there's 2 facing each other.
Why didn't you count the top ones? Like the ones above it?
Up here?
Yeah.
So I did these 2. I did do these 2. But I didn't do these ones because they're not against anything. Right? There's no brick here against this side. That's why I didn't count that. And I don't count these guys because there's nothing on this side blocking. There's nothing against. So when I was counting, I did count these guys. I might have just did it before you. I might have did it fast. Because there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Yeah. That's a good question. So the underneath, like if it's on the ground or not. In this case, we're just going to assume that this is like a floating object, so it's not on anything. But if we were doing a question where maybe something's sitting on the ground, we wouldn't need to paint that side, right? Because it's against the ground. But in this case, we'll pretend that it's like floating. So we do need to do the bottom. Awesome. I've shaded them all in. We're on D, total area of overlap. So when I'm trying to figure out the total area of overlap, one side is 1 centimeter squared. That's the area of one side. How many sides do we have overlapped? We have 18. So what we're going to do is we're going to do area of one side times the number of overlaps. I'm just putting OL for overlaps. So for us, that would be 1 times 18. That means we'd have an area of 18. Total number of area overlapping would be 18 centimeters squared. Part E. Part E says if the original object is dipped in paint, determine the area of the unpainted faces. We actually already did that. The unpainted faces, that's the overlap. So when you get to actual test questions, it's pretty rare that they call things the overlap area, right? They're going to refer to it in things like this. What's the unpainted faces, right? What are you not going to be covering? In this case, that is the overlap. So for us, it would just be 18. That's the area or surface area of the unpainted faces. Cool, that's a composite shape. They can get a little harder. This one's nice because they kind of drew it all out for you and they exploded it so you could see all the different shapes you have. But it does get a little trickier. We're going to try this one. This one's like a 3-dimensional one, meaning that like it's not just like a wall of bricks. Like last time it was just a wall. This one's kind of got some coming towards you, some going back. So it can be a little bit trickier to see all the shapes that are in there. They did do an exploded view for you to try to help. this question would have to have an exploded view for you because we don't know about the background on some of those. First question. So it says, complete the following for the composite object if each cube is 3 by 3 by 3. If it's 3 by 3 by 3, that means one face would be length times width. That's 3 times 3. That's 9. So one area for one side would be 9. The next thing we're going to do is we're going to figure out how many faces are overlapping. With that, some of them are easy, some are not so easy. We have to look back here at this shape that I'm coloring in blue. And we have to figure out if there's a shape underneath that. Same with this one in red. We have to determine if there's like a square under it. That's why they had to give you that exploded view. Right? Is it sitting on top of something or is it just like floating there? If you look at the exploded view, the blue one is the blue one there. The red one is the red one. The green ones are the ones that they're sitting on top of. So they do, in fact, have some that are sitting there behind them, which is important to us. Everybody sees that? The green ones are underneath those blue and the red ones. You just can't see them. They're hidden. If I keep trying to color code them, that means like this guy is this one right here. And this one is this one right here. This is the front one. And hopefully you can kind of see what they look like. This blue one, there's this blue one. Yellow is yellow. See how each box is kind of matching up? I personally, when it comes to like envisioning things like this, I'm really bad at that stuff. So like color coding it or shading it, really like labeling them helps me picture what the shape's supposed to look like. If I just looked at this, I'd have a really hard time, especially with depth perception, being like which brick goes where. And so sometimes coloring them might help. Like the green ones we can't see. They're underneath here. They're underneath the blue and underneath the red, so I can't see them. Yeah, for sure. Okay. The number of overlapped. If I want to figure out the number of overlaps, you have two choices. You can look at the main shape and do it that way if it works for you. You can also look at the exploded view if that works better for you. I'm going to look at the main shape because that's how my brain operates. So if I'm looking, again, this is easier to point than to draw it. So right here, we have two, right? There's this one, the bottom of the square, and the top of that square. So 1, 2. Then I have the bottom of this square and the top of the one behind it. 3, 4, 5, 6. Then I have the front back of this, 7, 8, 9, 10. Then these sides, 11, 12. This side right here, 13, 14. And this side right here, 15, 16. So I think there's 16. I'm going to double check, right? Just count through one more time to make sure. If it helps, you could look at the exploded view and try to draw them. So for instance, this one right here would be one side that's overlapped, and it'd be overlapped with the bottom of that box. So that would be 2. And you could keep counting them out. So whatever works for you, right? This is overlapped here. So is that under there. That's supposed to be an arrow somehow. Not even close to an arrow. That's a little better. That's an arrow. Right? So you can see each one kind of has 2. Again, if I did this, 1, 2, 3, 4, 5, 6 for under here, 7, 8 for under there. Then the sideways, 9, 10, 11, 12, 13, 14. There's that back guy in there for 15, 16. 17, 18. Yep.
What do you do? Like, it's hard to keep track of like how many overlaps.
Yeah, and like you can even see as I'm trying to do it, it's hard to keep track of them all, right? Like it is challenging. I would try your absolute best to do it multiple times so you can reconfirm if you're right or wrong. But there's no like foolproof system to it, which is what kind of makes it so hard, right? I think there's 22. I think I missed those front ones, right? Right here. I missed this one. I missed that one in there when I was counting it. And that's why I think it's important that you want to like double, triple count. So like if you look again, let's try again. Even after I counted the second time, I felt like I missed one, right? 22? All right, so let's try again. So if we're looking at this square, maybe this will help. For each square, let's see how many sides are overlapped on it. So looking at that square, how many sides are overlapped on it? One. Looking at this square right here, how many sides of it would be overlapped? Two. Awesome. Looking at this square right here, that would have the bottom and the side. And the top. 3. Looking at this square right here. Just the one side that's against it. Looking at this side right here, or this square, it would have the front of it, the side of it, and the back of it. So that would be 3. Looking at this square right here, it would have just the back of it for 1. This square right here, it would have the side, the left side, the back, and the right side for 3. This square right here would have the one side. And then we have the 2 squares you can't see, right? Those 2 squares in the background, which we earlier figured out were these guys back here. Right, these 2. And if I look at these 2, the front of this one would be overlapped. The top of it would be overlapped. The side of it would be overlapped. So that'd be 3. If I look at this guy, it would be 1, 2, 3, plus the other side for 4. So maybe if you're bad at these things, which I clearly am bad at these things, right? Like visioning things like that's not good for me. Maybe pointing at each cube and trying to think about it and then writing them down like I just did would work. And then you can add up all the cubes that are overlapping. There.
How would that one be 4?
There's this side that's in here. Like imagine there's a side right there because it's against this guy right here, right?
It just threw me off for you.
Yeah, because there's 3 that I can shade and then there's the one I can't shade. That's the hard part. You almost wish you could like turn it, right? Maybe that's a better system. Does that work a little better, Jake, you think? Like pointing to it and saying how many there are?
Well, like, yeah, if you put like an arrow to the square and just like count how many faces are on that square, the cube, it's kind of easy.
Yeah, maybe that's the way we do it. That worked better for me, for sure. Because then I keep track of it better. Yeah, like a dice would work for an example, yeah.
Just cross out a cube once you're done with it and you just move to the side and keep on moving.
Yeah, and like I said, if you're good at it, like some people just have an absolute knack for it. Like they can look at it and be like, oh, that thing's got 10 overlaps. I'm not that person. Like I'm one that I'd need to use that system for sure. Hit him. Yep. Now, if you want to figure out the number of overlaps, you're just going to add all those numbers, right? So 1 plus 2 plus 3 plus 1 plus 3 plus 1 plus 3 plus 1 plus 3 plus 4. If you throw it all on your calculator, you get 22. Maybe that's a better way to do it. In the future, that's probably how I'm doing it. I like that system. Awesome. We're going to try number 3. I'll keep shading in sides that are overlapped. But again, you can't see every side. So it's a little tricky. That's an overlapped. That's an overlapped. These tops are overlapped. Oh, no, they're not. Sorry. The sides of them are. Sides overlapped. Sides overlapped. Front is overlapped. This top's overlapped.
Is it for 14?
You missed us just going through all that. Yeah.
No, not that one.
It's
Never
burning.
Okay.
Oh.
Again, you can't shade all 22. You can't shade all 22 because you can't see all 22. If you then wanted to find the total area of the overlap, you need to take the number of sides times the area of one side. Right? So take the area times by the number of sides. I put OL for overlap. For us, the area of 1 was 9. We had 22 sides, so it's 9 times 22, which I believe is 211. No, it's not 211. 198?
Yeah.
198. I got it right, though. That's the area of the overlap regions. Sides that you wouldn't have to paint if you dipped it in paint, for instance. Part E says determine the area of the unpainted faces if you dipped it in paint. The area would be 198. You could just rewrite the math in there. Because it's the exact same question, just in a different phrase, right? Instead of saying the area of the overlap, they're discussing it as an actual word problem. So you took this thing, you dipped it, comes back out. How many sides did you cover? I didn't cover 9 area times 22 sides for 198.
Wow.
Awesome.
Did you go to grad school?
No.
I did.
Number 3, I want you to try on your own. So see if you can find the area of each face. See if you can find the number of overlap. Then see if you can find the total area of the overlap. So I'll give you a chance to try it on your own, and then I will go through it.
Is there a square?
Okay, so the first question it asked you to answer was the area of each face. So if you did the area of one face, what would you do, Jake?
2
Yep.
times 2.
Length times width, which is 2 times 2. So the area of one face was?
4.
Beautiful. Okay, for the number of faces that are overlapping, I'm going to do the system we just created. I'm going to point to a cube with an arrow, and then you're going to tell me how many sides are on that shape. So we'll start up here with this cube. How many sides are overlapping with that cube?
1.
Perfect. This cube.
3. No, sorry, 1.
Yeah, and then the one behind it. So there's this like invisible cube that's kind of back here, right? How many does that one have?
3.
Awesome. We'll keep going with the other ones. How about this guy?
2.
Agreed. How about this guy?
4. 2.
Agreed. This guy
2.
and the top one.
1.
Awesome. So that's all the cubes, right? I point to each one. I say how many sides on that cube are overlapping. We have 1 plus 1 plus 3 plus 2 plus 2 plus 2 plus 1. And we get a total of 12 overlapping sides. Awesome. Part C. Part C. The area of the overlap. So to figure out the total area of the overlap, Jake, do you want to keep going with this?
Yeah, so you times the number of overlaps by the area, and that means 12 times 4.
Perfect. So he said you take the area of one side and you multiply it by the number of overlaps. You told me the area was 4.
Yeah.
You told me there was 12 overlaps. Should get 48 as the area for the overlaps. Also, in part D, if the object is dipped in paint, determine the area of the unpainted faces. We're going to change this question a little bit to make it a little more fun. We're going to say determine the area of the painted faces.
Painted, bro.
Okay, so If you want to figure out the area of the painted faces, just because it'll be fun and I think you guys are
24.
looking to make this a little more interesting for yourselves. If you want to figure out the area of the painted faces, you need to figure out how many sides aren't overlapping. When you look at each cube, there should be 6 sides to each cube. In this question, there's 1, 2, 3, 4, 5, 6 cubes. That means in total, 6 cubes times 6 faces. In total, there was 36 faces. We know that there's 12 overlap. So if we subtract those 12 overlap, we find that there's 24 faces that need painting. The bottom counts as a face that you paint.
I know.
If it said like if it was only
There's 7.
Yeah, so if there was something 1, 2, 3, 4, 5, 6, 7, there is 7. There is 7.
So 44.
Good save, Brandon.
Yeah, Brandon.
There we go. If say the object was on the ground, say like I wanted to paint a wall, I wouldn't paint the ground. So you're right, you would subtract that. The area of the painted faces would then be the area of one side, which was 4, times the number of sides that would need painting. This would be 120. That's how much we would end up actually painting. Any questions about that? It's a little trickier, and we will eventually get to that stuff. Just figure it might as well be worth a shot looking at it now. Okay, example 4. I want you to try on your own again. If we look at this, we'll start off simple. It says the area of one face. The area of one face of a cube is length times width. For this question, length times width is 5 times 5. That means 25 is the area of one face of a cube. The number of overlaps. This is trickier. The reason this is trickier is because the things aren't perfectly on top of each other. Right? If we look up here, you notice that that top cube's almost like in the middle of it all. It's not perfectly over any of them. So when you're doing that, our little system of pointing at a cube might not work. Because if I say, well, how many does this guy have overlapped? It only has a little bit, like a portion of it. But if you look at all these guys, so if we include this one and the one back here, and you added all of their portions together, how many would be overlapped? That would be one full side that's overlapped, right? It has to match up with this top one that's on top of it. So for a question like this, rather than saying, okay, how many are overlapped for each cube, I'm going to say how many are overlapped for each like layer. Right? I have the first layer, the top layer, I have the middle layer, and then I have the bottom layer. And it might be easier to think of it like that because they're not perfectly on top of each other. So if I look at the top layer and I said, how many sides on that top layer are overlapping? There's only one side, right? The bottom of that top layer. If I look in the middle layer, the blue layer, and I said in that layer, how many sides would be overlapped? On the top of this blue layer, there would be 1. But on the bottom, how many would be overlapped? There'd be 4. So in total, that layer would have 5 covered faces. 1 on the top, 4 on the bottom. If I look at the yellow layer, on the top of that yellow layer, how many total would be missing?
4.
Yeah, there'd be 4. Right? The 4 from the thing on top. So for questions like that where it's not perfectly lined up, it might help to just look at it as chunks, like entire levels of something. For us, the total number of faces would be 10. 1 on the top. The middle layer's got 5, with 1 above and 4 below. And the yellow's got the 4 on top of it. The total area of the overlap would be the 10 sides times the 25.
You have the other ones.
Not 10. Which one am I missing? Oh my goodness. I'm missing all those insides. Thanks for saving me.
Good teacher.
Why did you say anything faster? Right? Because I still like the tops and the bottoms. And that helps me get those numbers. So I'm still going to look at this and say the 1's got the 1 bottom. The blue had the 1 on top plus the 4 on the bottom for 5. And the yellow still had the 4 on the top. But that's only doing the tops and the bottoms of squares. It's not doing all the inside layers that are on top of each other. So looking at each thing, I'm then going to do how many sides are there together. For instance, if I look here in the blue one, and I look at this corner brick right there, that corner brick would have 2 sides that are overlapping. On the inside, right? I'm talking about just the sides, not the top and the bottom anymore. If I looked at the other one, that would have another 2. This one would have another 2. And that back corner one, which we can't see, would have another 2. So that means when it came to that layer for the sides, it'd be 2, 4, 6, 8. There'd be 8 sides in that middle layer that are overlapped. For the bottom one, I'm going to do the same thing. So I've already said the 4 on top for this yellow layer. Now I'm going to talk about sides. So if I look at that corner block, there's 2 sides to that corner block. If I look at this one, it would have 3, right? 1 on the left, 1 on the right, and 1 in the front of it. This one would have 2. This one would have 3. The back corner would have 2. And then we have a whole bunch of blocks we can't see, right? We got 4 blocks that are not in the picture. You have to make up your method of how you want to do that on those back blocks.
What if you just sit it up there?
Gotta pretend they're there. So if you're looking at those back blocks, you've noticed hopefully that the middle ones always seem to have 3. So there's a middle one over here for 3. There's a middle one over here for 3. And then we're missing that back corner. The corners appear to have 2. So that means that back corner would be 2 more. And then there's the middle cube in the center of it all. That center one would have all 4 sides of it covered, right? So that would be 4 more for the middle one. Right, but we already covered the tops of everything. I'm just looking at sides. If you were to add all those numbers, that would give you the number of overlap sides. So for us, if you did 1 plus 5 plus 3 plus 2 plus 3 plus 4 plus 2 plus 3 plus 2 plus 4 plus 2 plus 3 plus 8, you get 42 sides that are overlapped.
No, you have to put 0 there.
Questions like that will require you to definitely take your time And I did it on the previous questions. Like I myself do it multiple times because I know it's something I'm not good at. Right? I always miss sides. I always miss something. So I do it multiple times so that I know I'm eventually right. If I get the answer 2 or 3 times, the same answer, that's when I stick with an answer. If I keep getting a different one, then I keep going until I start repeating an answer. So if I looked at a question and I got 10 for this one, and then I tried again and I got 30, tried again and got 40, I would just keep trying again until I started repeating an answer and then felt confident with it. Right? Like just keep going.
What if you keep repeating the answer, but you're making a mistake?
Right? And that happens. Right? So take your time, try things multiple times. It's going to be important with this stuff. The total area of the overlap. Each one was 25. We have a total of 42 things. If you throw that in your calculator, 25 times 42 would give you 1,050 as the total area of the overlap region.
That's a
Again, if we wanted to do the painted side, so let's scratch out on. Let's try the area of the painted side. You would need to do the area of all the cubes and then minus the area of the overlap. If you look, you need to count the number of cubes that there are. There was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. There's 14 cubes total. Each one has 6 sides. Each area of a side is 25. That would give me the area of all the cubes. It's going to be a big number. 2,100. That's all the cubes. The 6 came from there's 6 sides to each cube. So 14 cubes. Cubes. 6 sides. 25 is the area. That make sense? Yeah.
What if all the squares that make the squares count as squares?
We lost squares. So that'd be 2,100 minus 1050,
Which gets 1050.
which gives you 1050.
So all that work was unnecessary.
All that work for nothing. Just to get the same answer.
Come on, man. Mr. Kennedy.
Yes. This big cube. Looks like a Rubik's Cube. His is a big Rubik's Cube. Yeah, so if you looked at it, and you wanted to figure out how many cubes are actually in that thing, it's like doing the volume of something.
125.
How'd you get that?
There's 25 on each section. You just count quarters.
Yeah, so there's 2 ways to do it, and that's kind of more of a logical way, which is good. So what she's saying is if you look at a section, for instance, let's look at the top section. The top section has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. The top section has 25 things. Each section then would have 25. So this is 25. This layer would have 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 25. For a total of 125 total cubes. So that is definitely a way that you could tackle that problem. Figure out how many's on the top layer, and then every layer would have that many cubes to it. Right? And that's what we're doing. So top layer 25, so each one has 25. And then just add them all up. What's another way you could do, Jane?
I did 5 by 5 by 5, so you do 5 being the top layer, 5 being down, and then there's 5 in down. I just did 5 by 5 by 5.
Yeah. So the way that Darian did this is actually the same, except he's just breaking it down a little bit further. So he's looking at all these things, and he's saying, if I'm looking at one side of these cubes, I'm going to try to erase all that. That's a lot. For instance, this side. That side has 5 cubes to it. It then has 5 cubes deep. And then there's 5 cubes stacked up total. That would be 5 times 5 times 5 for a total of 125 cubes. It's called the volume of something. Right? If you ever want to figure out how much total is inside of a shape, length times width times height would give you the answer. If you do it the way that Kessa described it, which it was like there's this many and then how many of those, it's the exact same process, right? You did 5 by 5 to get your 25 for the top layer, and there was 5 of those. Same idea, just different way of tackling it. Correct? Yep. So the total number of cubes in the object, 5 times 5 times 5 for 125 cubes. Awesome. Doing this and figuring out painted, unpainted, overlap, unoverlap. There's different ways of tackling that problem. Sometimes it might be easier to figure out how many are not overlapped. So for a question like this, in my opinion, it's probably easier to figure out what's not overlapped. And that kind of makes sense. If I look at this, and I wanted to figure out how many sides are not overlapped, I would do one side of the cube, like the big cube. So I would say like what we had done before was that there was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. I know that one side has 25. 25 shown faces. And then I could just do that for every side of this big cube. So this side has how many? Another 25. This side has how many? Another 25. This back side that you can't see has 25. This bottom that you can't see has 25. And this back side you can't see has another 25. So it might be easier to do surface area as if it's just one big cube. And then you could figure out how many total faces are showing. In this case, it'd be 1, 2, 3, 4, 5, 6. 6 times 25. It'd be 150 total sides showing. I think that's the easiest way to do it, personally. If they were to ask me how many sides are showing, or if they ask me how many sides aren't showing. Because then I could use that info to subtract it away from the total number of sides that they're expected to be. They also have some random questions that we're going to answer. So it says, how many cubes have 3 sides showing? So for instance, a cube that has 3 showing would be your corner cubes. Now we're talking about little cubes, right? This guy right here has 1, 2, 3 sides showing. This one over here would have 1, 2, and a third side showing. This one would have 1, 2, 3 showing. All the corners would have 3 showing. So how many cubes have 3 sides showing? 8. The 8 corners. How many cubes have 2 sides showing?
36.
2 sides showing would be a cube like this. Right? It's on a side, but it's not in the corner. So if we look, there'd be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Oh, I'm lying. When we're counting a cube, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's 12 cubes that have 2 sides showing. But now I don't want to count them over here, right? Because I already counted that as 1 cube.
You just messed me up then.
This would be another one right here. Another one right here. Another one right here. Another one right here. Here, 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 here. I'm only missing one set that I can't see. I'm missing the bottom back left corner, like back there. There would be 3 more back there that I can't see. Right, so it'd be 3, 6, 9, 12, 15, 18. I still did the same mistake.
It's 30.
Yeah, let's redo this.
Let's go, Mr. Kennedy.
Holy man, hey?
Just messed me up there.
Nobody's a kid quick.
Let's try this again.
He's not mistaken.
Honest mistake. Because I did the same mistake again. I counted 2 on the left side there. Pretend I've told you nothing. Erase your brains.
It hasn't been functioning.
Yeah, good, perfect. Like that Men in Black thing, right? Like the scan. Yeah, I'm gonna scan that right now. So you forgot everything I said about 2 sides, and we're gonna try it again.
See,
Cubes that have 2 sides showing. This cube has 2 sides showing. This cube has 2 sides showing. This cube has 2 sides showing. This one, this one, this one. These all have 2 sides showing. So that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That covers those top 12. Then there's cubes on the side that are showing. Yeah, go. This one, for instance, those have 2 sides showing. Back here would have 2 sides showing. Over here would have 2 sides showing. And then there's the back corner that we can't see, right? The back corner would be 3 more. On the bottom, we would have 3 on all the in-betweens. And again, the 2 back corners that we can't see on the bottom. That was a little better. That gives us 3, 6, 9, 12. 12 more in the middle. 12 more on the bottom.
You could just say there's 6 of them and go 3 times.
Yeah, so you do 6, 12 times 3, yeah. Like 12 on the top, 12 in the middle, 12 on the bottom. But there's 36 that are showing 2 sides. The number of cubes that are showing 1 side. A cube that's only showing 1 side would be like this cube right here in the green. If you look, each side has a total of 9 that are showing 1 side. Since there's 6 sides to this thing, it'd be 9 times 6 for a total of 54. There's 54 one-sided shapes. Yep.
You would count the bottom.
Yep, like those bottom 9 you would count. Same with those back 9 on the 2 back corners that you can't see. How many cubes would have no side showing?
27.
How'd you get 27? Joey.
No, it says 0 sides and they'll say cubes.
Oh, never mind.
There's 9 by 6.
Let's do no. How many cubes have 0 side showing?
There's 27 because if you go down from 27, you go 3 more lines.
Yeah. So
It's 9 by 6 again.
if you want to figure out how many squares or cubes, if you tried to figure out how many cubes have no sides showing, there's 2 ways you could do this. The way that Joey was describing was imagine the cube inside the cube, right? So if you looked inside here, you erase like the top layer, the bottom layer, and all the side layers, you'd be left with a 3 by 3 by 3 cube on the inside of that thing. The volume of that would be 27 because 3 times 3 times 3 is 27, which is correct. Another way you could do it is you could take the total number of cubes, which we know is 125, and you could subtract how many 3-sided there are, which was 8. Subtract how many 2 sides there were showing, which is 36, and then subtract 54. And you would get 27 cubes that ended up showing none of their sides. Both methods are legitimate. If you can picture that on the inside, way faster way to probably do it. No, it's the number, how many cubes have 0 side showing.
But then there's a cube inside.
Right, but we already counted because we had volume. Right? We did length times width, 3 times 3 times height, which is 3. Yeah. It's kind of tricky because it's like part B, like 4 of part B. It's okay. Please do, yeah. Yeah, if you gotta go to the bathroom, go to the bathroom.
Yeah, but why'd you say please do?
Okay. If I wanted to figure out the area of the overlap of this composite shape, it's not cubes anymore, so I can't just do the area of one side of the cube and just keep multiplying by that. Like, that's a handy trick, but it only really works for cubes. You are going to get shapes like this, where you have different types of shapes against each other. We didn't even get close to where I wanted to, which would be things like this. Okay, so we're going to have a lot that we're going to have to pick up next week on Tuesday. For this guy, we'll at least start it off. A lot of people can get the first side that's overlapping. If you look, you have this cube against, this rectangular prism. If you imagine, it's this side right here. And if you wanted to figure out the area of that side, hopefully you'd be able to identify it's going to be the same as the area of this side. Right? They're the same sides. That means if you did 3 times 6, that would give you the area of the overlap from that rectangular prism. However, what people miss is that there's also overlap in the big shape, the big box. They kind of demonstrate that on the exploded view on the right. So over here in the blue, they've shaded in for you on the little rectangular prism. But on the big rectangular prism, there's also overlap that you wouldn't need to paint. There's that little box in red, which would be the exact same, right? It would also be 18. So when you ask what's the total amount of overlap in the entire shape, it would be 18 plus 18. If you did 18 times 2, that's the exact same idea. For a total area of 36 that's overlapped between those two shapes. Right. Jake.
You could also do like 3 times 6 times 2.
Yeah, so if you did 3 times 6 times 2, so 3 times 6 would give you the area of the one face, times by 2, because you know there's 2 faces. That would definitely work.